Hello everyone, welcome. In this video, we will discuss the procedure for solving the following integral, the integral from 0 to infinity of sine of x over x dx, using Feynman's technique. What's interesting about this integral is that we are very limited with the techniques we can use to evaluate this integral, since there are no antiderivatives, substitutions, or integration by parts we can use. However, we will see that by using Feynman's technique, the value of this integral can be found fairly methodically. Feynman's technique is a very powerful method for evaluating definite integrals, and at its core, it exploits the fact that any integral can assume an equivalent form simply by adding 0 to any part of the integrand, or by multiplying any part of the integrand by 1. Let us focus on the latter and multiply the entire integrand by 1. The essence of this technique is to leverage the fact that we can accomplish obtaining a factor of 1 next to the integral in an infinite number of ways. For example, instead of 1, we can write sine pi over 2, which still does not change the integral, or cosine of 0, or e to the 0th power. All of these are equivalently 1, which means our integral does not change. Let us focus on the last instance of this, e to the 0th power. We know that our integral has not changed, and we should notice that there are even more ways of writing this without changing the exponent of 0. For example, we can replace 0 with 0 times x, which is still an equivalent form of the original problem. What we are now going to do is allow ourselves to write the same integrand in an even more generalized form. Let us replace 0 with the parameter b, and think of the value of this new integral as a function of this parameter, which we will call I of b. We also acknowledge that when the parameter b is 0, the value of I is simply equal to the original problem statement, the integral of sine of x over x dx. So now that we have this alternate way of expressing the problem, there is still one major issue with our equivalent integrand, and that is it does not converge as x goes to infinity due to the e to the positive x factor. We can fix this issue pretty easily by simply just flipping the sign on the exponent, which results in the exponential factor going to 0 as x goes to infinity, producing a converging integral. So how is this modified form supposed to help us evaluate the original integral? Well, because of our specific selection of the factor of 1, e to the negative bx power when b is 0, we can actually now take advantage of a very convenient event that takes place when we take the integral I of b and differentiate it with respect to b, producing I prime of b. When we apply this on the right-hand side, since I is only a function of b, all x's are treated as constants, which means we could take the partial derivative on the right-hand side with respect to b, ending up with the following. This is especially convenient because the x's can now cancel, leaving the resulting much more manageable integral, which can be somewhat easily evaluated using integration by parts. At this stage, we should follow the usual integration by parts procedure by choosing the appropriate u and dv and applying the integral of dv every time v occurs and derivative of u every time du occurs. When we follow this procedure, we see that we actually end up with a second term also needing another integration by parts, which means we would have to carry out integration by parts once more. While this is certainly doable, there's a much easier way to deal with such types of integration by parts problems, and that is by using a technique known as tabular integration. What we would do is we take our original integrand, which is made up of two functions multiplied together, and create a table with two columns, one that we will label d and one that we will label I. For the d column, we will populate the first row with a function from our integrand that we wish to differentiate. And for the I column, we will populate the first row with the remaining function from our integrand that we wish to integrate. Most of the time, the selection of which function to differentiate and integrate is strategic, but in this case, it does not matter which function is which. Next, we will differentiate and integrate each of the functions based on their designation, d or I. We can do this for as long as we'd like, but in this case, we will stop printing the functions after the third row. Next, a very important step, we print an alternation of signs in front of the first column, starting from positive, and alternate as far down as the table is generated. What we've done here is very valuable, since we've effectively produced all of the essential components to the integration by parts formula. We can generate the expression for the integral by drawing a diagonal arrow between the first and second row as such, and multiplying all of the factors involved, which produces the first term in our evaluated integral expression. We do this once more with the second row, producing the second term, and we quickly realize this can go on forever, since in this unique case, none of these derivatives or integrals ever go to 0. And this is true, which is why when we are presented with such an instance, we can take the third row, which includes the first instance of the trig function repeating itself, and change the direction of the arrow and have it point horizontally instead of diagonally. This is a way of terminating the terms in the integration by parts formula. However, if we were to carry out the multiplication in the horizontal direction, the resulting product must exist within an integral rather than having no integral present like the first two terms. We now have this expression which is supposed to represent the indefinite integral of interest, the integral of sine of x times e to the negative bx. The problem is, we have seemed to express this in terms of another new integral. The point of this is more apparent when we observe the fact that both of these integrals have identical integrands, and therefore are like terms, which means we could simply collect the integrals on one side and then isolate the integral we are interested in, thus successfully evaluating the integral. We can then turn our attention back to the original differentiated problem statement I prime of b, which is the negative of the integral that we just found the antiderivative of. We can divide by -1, matching the form of I prime of b, and then evaluate the antiderivative from 0 to infinity after making some simplifications for clarity. After doing this, we see that all terms go to 0, except for the last one, which results in the following expression for I prime of b. For compactness, we can multiply every term by b squared, ending up with the following. At this point, it's important to not lose sight of the original objective. So far, we have formulated the problem such that the integral I, when b is equal to 0, is the value of the integral we are trying to solve. And as for now, we don't have an expression for I of b, we only have an expression for I prime of b. So we could simply integrate I prime of b with respect to b, producing an expression for I of b. On the right-hand side, we should fairly easily recognize the antiderivative of -1 over b squared plus 1, which is simply negative arctangent of b plus c. We've now developed an expression for the original modified integral in terms of b, but there is still one piece of unfinished business. The integration constant c that came up from the integration of I prime of b is unknown at this moment. We can actually quite easily determine the value of c. We should remember that the function I of b is simply just equal to the original modified integral, and by strategically allowing b to go to infinity, which means arctangent of b is pi over 2, and on the right-hand side, the e to the minus infinity factor forces the entire integral to vanish, which means c is simply equal to pi over 2. We're now at the final step in our procedure, where we simply need to remember that when b is equal to 0, I becomes the original problem we are interested in solving. So after plugging 0 in for b, we end up with I of b equaling pi over 2, which is the solution to the original integral.